Thank you all. I'm saying it in my name and in the name of Lucas, because we are glad to see you all in this auditory. So this section today will be about the work of Lucas Chagas Lima do Carmo. And Lucas will present his work, and after we have this a protocol in 3 parts. The first part, Lucas will give us like a oral presentation. In the second part, we have argumentation. In the third part, we have the jury that will attribute some kind of scores. At this point, we have approved it or not for the work of Lucas. We want to say thank you also to the jury members, Professor Saad Khan, Professor Fabio Murakami, and Professor Agnes Scheer. Lucas, you have now something about 50 minutes to present your results. After that, we have like 10 minutes for has a break, and after we continue with the second step, named argumentation. Thank you very much.
Foi? Sorry about that. Okay, so my name is Lucas Chagas Lima do Carmo. I will be presenting a presentation today. And okay, I'll be presenting my dissertation today. One. Okay. Sorry about that. Microphone wasn't working. So my name is Lucas Chagas Lima do Carmo. I'm going to be presenting my dissertation today and then defending it. My dissertation is named Cosmetic Emotions Physical Stability Screening by Means of Rheology. And this was a work that was a combination of efforts from multiple parties, such as Grupo Boticário, the chemistry department, and CAPES that has funded the research, and it does fund most of the research in Brazil, and of course the Federal University of Paraná. I am a student from the Pharmaceutical Science program, and this presentation will be divided in these sections. First, the introduction, where I'll present the subject, and then a little bit of a review of the concepts and methodologies. The objectives, materials and methods, where I'll explain how the experiments were performed and how they were analyzed. The results and discussion will be divided in 4 parts. First, the classic methods of stability assessment for cosmetics. Second, the influence of oil content on rheology. Third, the influence of storage time on rheology. And then finally, the rheological thermal analysis, which was the main experiment that was used to perform the screening. And then finally, the final considerations and my personal conclusions about the project. Okay, so firstly, we have to understand that the cosmetics industry is a multi-billion-dollar industry, not only in Brazil, but also in most of the countries throughout the world. It has been growing almost constantly and linearly over the past 10 years. And this growth is a result of the consumers' interest that is growing on these products, but also their expectations are also growing. So the industry has come up with is having new challenges in producing different formulations and producing different products to meet those needs from the consumers. Now, with all that demand from the population, some challenges arise. And the first one, and I think that the most important one, is that these products, they need to be evaluated on their physical stability, their quality, their biological safety. And here I'm gonna try to explain how to improve the physical stability assessment of these products, so companies start to reduce the time that it takes to predict the stability of these products. Now, the main method that is used today, in Brazil at least, is this guide that was formulated by the National Health Surveillance Agency here in Brazil. And this guide has some methodologies that are not necessarily new methodologies, not very complex methodologies, that in most cases don't have the capacity to assess prematurely the stability of the products. They only assess the properties of these products over the time that they're being analyzed. So in this guide, there's not a lot of predictive tests, and most of the methodologies takes up to 90 days of evaluation to determine if a formulation is stable or not. And this time is not efficient for the industry. It is not very economically viable. So our main goal here is to try to reduce that time under a period of a couple of weeks or maybe a couple of days. These products, they use these methods to evaluate the stability of creams and lotions and gels and shampoos. And the one thing that creams and lotions have in common is that they are emulsions. And emulsions are a colloidal system of two liquid immiscible phases. They can either be of a oil in water phase, represented on the left, or water in oil, represented on the right. And they usually have the droplets that are dispersed, usually have a size of 1 micrometer to 100 micrometers. And these are the structures. This is the system that composes creams and lotions that are used both for cosmetics and pharmaceutical products. Now, these emulsions, they can be stabilized by different types of stabilizers, different types of molecules or particles that can be used to stabilize them. So here on A, we have droplets of oil inside a continuous water aqueous phase that are stabilized by some type of ionic mechanism. And then in B, we have droplets that are stabilized by solid particles. And on C, we have droplets that are stabilized by polymers. And then on D, we have droplets that are stabilized by a molecular surfactant, which is a type of molecule that have properties that can interact between aqueous and oily phases and then reduce the interfacial tension of the interaction between them. And then on E, we have multiple emulsions where you have aqueous phase dispersed in an oily phase and then dispersed on an aqueous phase. And in F, the same, but with multiple droplets. Now, emulsions are thermodynamically unstable systems. They are inherently unstable systems because to form them, you need to add some energy to the system so you can generate these droplets. So on this graph here, we have on the x-axis time and then the y-axis the energy. And this is just a relative energy. But when you're producing emulsions, you're adding energy to the system. And to explain the thermodynamics of emulsions, we have to make two assumptions. First, is that the enthalpic term here represented by delta H is directly proportional to the surface area term. And then the second assumption that we have to make is that the entropy term times the temperature is much, much smaller than the surface area term, which allows us to claim that it's that is not very doesn't determine the relationship of energy in this equation. So it's negligible in this case. So the result is this equation, free energy equals to the interfacial area between the two phases. So in this case, when you're adding energy to the system, we form droplets, and the Gibbs free energy increases, the surface area increases, and the entropy increases as well, but it's negligible in this case. So as time goes by, we see that the tendency of the system is to decrease the free energy. And this happens by coalescence and aggregation and flocculation. And finally, the result is that we have the two different phases separated all over again. But if that is true, if all emulsions are thermodynamically unstable, then how do we have creams and lotions that are stable over time and they take weeks and maybe months to destabilize? Well, we can add a barrier, a kinetic barrier, between the droplets that prevents them from coalescing and flocculating and aggregating. This barrier is mediated by those ionic systems that cause the repulsion between the droplets, or polymer systems that provide a steric hindrance between droplets, or even in the case of the emulsion studied, thick layers of surfactants that are surrounding the droplets and prevents them from coming too close together and destabilizing. Another strategy is to add a polymer that is cross-linked to prevent droplets from migrating and prevent them from colliding with themselves. And this equation here is the general relationship that we have for emulsions when very diluted. This is the fraction of dispersed phase in the total phase. So for emulsions that are very diluted with a phi less than 0.02, we have this relationship where the dispersion viscosity, the continuous phase viscosity, is inversely proportional to the creaming velocity. And then we have the radius of the droplets that also has an influence on the velocity of creaming or sedimenting, depending on the density. And the density difference between the aqueous and continuous, the internal and external phase, is also relevant for diluted emulsions. But the same principles apply for emulsions that have higher concentration, but other factors come into play as well when you have more droplets dispersed. So here's a summary of all the breakdown mechanisms of emulsions. Depending on the nature of the dispersed phase, it can either cremate or go up, migrate towards the surface, or sediment. And there's a phenomena of auto-ripening, which is the increase of droplets. There's a phenomena of flocculation, which is the aggregation of these droplets. And then the final result is the complete separation of phases here, shown by this top part of the figure. However, on the creams that were formulated in this project, we not only have dispersed droplets, we have structures that are formed because these components are part of it. The cetoserial alcohol has the capacity of forming bilayers, surfactant bilayers that looks a little bit like this. So on here, on the figure on the right, we have these structures here. There are bilayers of surfactant that can branch out and can aggregate and form multiple layers of surfactant on a crystalline liquid phase, represented by C here, or maybe surrounding droplets, represented by those structures surrounding the droplets in E. And the properties of these creams can be described by both viscosimetry and rheometry. Now, for viscosimetry, we are only measuring the flow properties of these materials, and we're not measuring the elastic and viscous moduli of these materials. And what is the difference? Well, the difference is that this flow properties don't correlate well to the structure in its resting state. So by using rheometry methods, we can measure elastic and viscous properties that are more correlatable to the properties of the material when it's resting, when it's not flowing. And it's usually non-destructive method because it doesn't shear the sample as to so hard as to destroy the internal structure, and is usually used in small stresses and shear rates. So in rheometry, you have the concept of elasticity and viscosity, and to exemplify, here on the top illustration, we have a material that is completely elastic. It's purely elastic. And we can see that the stress, the shear stress on the black line is completely in phase with the deformation of the sample, which is on the orange line. So this is purely elastic because there is no lag between the tension applied and the response of the material. Now here for purely viscous materials, we have a 90-degree phase angle between the tension that is being applied, the shear stress that is being applied, and the deformation that the sample is exhibiting. And for all viscoelastic materials, which are the most materials are viscoelastic, we have a difference, this shift in the angle is bigger than 0 and smaller than 90. So for materials that have a delta between 0 and 45, they're more elastic, and for materials that have more viscous properties, they are between 45 degrees and 90 degrees. And here are the experiments that we are using to characterize these motions. The first one is the amplitude sweeps, where we increase the tension as a function of time, and by that we can measure some variables like the cohesive energy of the structure, which is the measurement of the energy of the dispersed structure, the yield stress, which is the stress where the dispersed structure starts to break down, and the linear viscoelastic region, which is a range of stresses where the sample did not deform irreversibly. So this is the yield stress represented by this dotted line, and everything under that stress is the linear viscoelastic region. We also have frequency sweeps where we measure the relationship to time of these structures. So the relaxation time, that is the inverse of the crossover point determined here, is the time that it takes for the structure to relax in a determined stress condition. So it's a constant stress being applied over different frequencies. The complex viscosity is the viscosity of material, but it also takes into consideration the elastic modulus. And we have something called the gel structure parameters that are the values that represent the extension and the strength of the gel network of emulsions. Now, the most important experiment that was designed for the project was a rheological thermal analysis, where we set a constant, like Brummer, we set a constant shear rate, shear frequency, and shear tension, and vary the temperature over cycle. So in 2000, Brummer found that if you have temperature cycles being applied over the samples, if G prime and G double prime, that is the elastic and viscous moduli, are constant over time, constant in temperature range, and constant with changing stresses, and that stress can be either temperature or humidity or storage time, then you have a stable formulation. So here on the top left, he described this formula as being a stable formula. So here we have G prime on the y-axis and G and temperature on the x-axis. So over several temperature cycles, he found that G prime for these samples were constant, which was not true for other samples that have varying values of G prime over the temperature cycles. And then a little bit later, Tadros claimed that studying the rheological properties over as a function of temperature cycles or temperature is essential for the full evaluation of cosmetics and emulsion stability. Later, Brummer published in his book in 2006 a larger scale example, larger scale study where he showed that for distinct storage times, these emulsions here on the top had a higher variance, and then these ones were more stable over the temperature. And he claimed that this was one way of assessing emulsion stability. And then this method started to be used by more researchers, like Laka and collaborators, and then later it started to show up on handbooks, and people started to notice the methodology. And then the most recent studies found also came to the same conclusions, that low thermal stability as function of G prime and G double prime changes. They discovered that this for food products, and the same here with a water and oil emulsion that was used as a cosmetic product. So the variables that we evaluated over time for the samples that were formulated are the G prime and G double prime curve profiles, the crossover frequency, use stress, complex viscosity, cohesive energy, weak gel model parameters, and then the rheological thermal analysis parameters. And then we also measure the droplet size distribution over time and difference between samples, stability over centrifugation, droplet morphology, pH, conductivity, and sensory properties. These on purple here are the ones that are usually used in the cosmetic industry. So the objective was to develop a protocol of rheometry experiments to predict cosmetic emulsions' physical stability. And then the specific objectives were to prepare oil and water cosmetic emulsions based on the Brazilian pharmacopoeia that are stable over the experiment duration, promote the structural instability of these products that were developed, conduct accelerated structural stability assays, long-term shelf life stability assays, and then finally correlate the rheological properties and parameters with the emulsion stability. So the final proposal of the project was to go from here, the current model that is used, where we have 30 to 90 days of stability studies, to make a decision whether or not they are stable, to reduce this time to one screening day and reduce the time that it takes for this decision to be made in the prototyping stages or the formulation stages and development stages. So we chose a non-ionic cream that is described on Brazilian pharmacopoeia. And to stress this cream, it is a very stable cream. It is known for decades to be very stable. And to destabilize, we increased the concentration of mineral oil to see if that would destabilize these formulations over time. And we chose, we produced several, I'm sorry. So the methods of producing these creams is described on the national formulary of the Brazilian Pharmacopoeia. And both phases were oil and water, and aqueous phase were heated to 80 degrees. And then the aqueous phase was poured over the oily phase at 5.5 milliliters per second at 50 RPMs. And then the emulsion refining was done using a Silverson high shear mixer for 2 minutes at 3,000 RPM. And then finally, for the cooling stage, it was immediately immediately agitated at 50 RPM with a helix paddle for 30 to 50 minutes until it reached roughly 25 degrees Celsius. After that, these formulations were covered with PVC paper, and they were stored at an ambient temperature for maturation. So 7 formulas were produced. For A, B, C, and D, we produced 3 batches. And these numbers here are the oil fraction and the mass fraction of these formulations based on the mineral oil that was added to the formulation. So as we increased the oil concentration, we hoped to find more unstable formulas. And for each one of these batches and each one of these formulas, we measured we did all these tests: the microscopy, Fraunhofer diffraction to measure the size distribution of the droplets, oscillatory rheometry to determine the rheological parameters, sensory tests, including olfactory and visual tests, centrifugation to have an accelerated study of phase separation, and then pH and conductivity. All these tests were performed in 1, 7, 14, 28, up to 182 days at ambient temperature, and for 14 days stored at a climatic chamber at 40 degrees Celsius. So for the first part, the classic methods will be discussed. So here on this table, we see that these formulations that are on this table with these batches were the one that separated phases macroscopically and by centrifugation. So on the middle column here, we see that batch C of formula D separated phases within 24 hours of production. And for all of these other samples, we saw phase separation at 28 days for the batch B of formula D, age A 42 days, and IA 56 days by centrifugation, but not macroscopically. All of these formulas that were stored, at higher temperatures, at 40 degrees Celsius, we saw separation within 14 days of storage. So here is a summary of all the formulas that failed this test and the ones that passed. So A and B passed, C, 2 batches failed, and all the rest failed. And this is one of the first methods that is used to assess stability. Here on measuring pH values, we took the average between these points here on this gray rectangle and the standard deviation. So the areas shaded in yellow are the areas where points were between plus or minus 1 standard deviation and 2 standard deviations. And the red shaded area here on the top and on the bottom are the formulas that were over 2 standard deviations or under 2 standard deviations. And we saw that for formulas D and H, under 91 days, they had already shown a not interesting profile on the pH values because they were varying too much. And for other formulas, at 182 days, we saw that other formulas had failed this test. But again, this is not a method to assess stability of the formulations, just to determine whether or not the pH is varying. The only reason we would have to reprove these formulas if they reach a pH value of under 4, which is not compatible to the skin. So here is a summary of the formulas and batches that failed and the ones that didn't. But this does not indicate stability in any way. So for the microscopy evaluation, here we have diluted samples at 1% mass volume. And we can see that formulas with lower oil content, like A, have a different morphology and different size distribution than for D. And this was expected because as we added more oil to the formula, we expected to have larger droplets, and which was what happened. So we can see the profile of A and D, and then B compared to F. Here we also see that droplets are very small, and there's not a lot of deformation in them. But for F, with a higher oil content, we see that they are very deformed. They have this strange morphology, and the width of the size distribution is much larger. And then here for C and H, we can see that C already has some larger droplets, but the morphology remains mostly intact. But for H, we see some deformed droplets here and here, and some aggregates here on the top that can indicate that these formulations have some type of gel structure that makes them that helps them stabilize. With a higher magnification, we started to see that there is a shadow surrounding the droplets. And this shadow, represented here by this letter A, led us to believe that the reason these formulations were highly stable was because they had a thick layer of surfactant over on the interface between aqueous and oily phase. And we can see that there are also these structures that could be a result of surfactant buildup and surfactant crystallization. We also see the same profile for formula B, and we see the same thing happening for several of other formulas. So we investigated using polarized light microscopy, where we found that these formulas actually had these crystalline liquid phases surrounding them, which is identifiable by these B refringent structures here shown by the white color. And this happened for several of the formulations. And actually, there is a large buildup of these liquid crystals on the interface. And this happens for most of the droplets that are analyzed, if not all of them. For the Fraunhofer diffraction sizing, we saw that the formulations with higher oil content, have a larger size distribution. So here on the orange line, we have the distribution for formulation D. And C and B and A, we can see that A has a smaller size distribution than for formula D. And we also saw that over storage time, so here on yellow, 1 day of storage, on orange, 14 days of storage, purple, 28, and this dark purple, 182 days, we see that there's not a lot of difference between the size distribution on different storage times. We also saw that there is some difference in the batches when we take the volume-weighted mean diameter of these formulations. We see that batches have different sizes, different mean sizes. So for batch C of the formula A, we have somewhat smaller sizes than the other batches. For the batch C of formula C, we have larger sizes over the storage time. And for formula D, we see that the batch C has even larger sizes when compared to batches A and B. And this is obviously noticeable because it had separated phases under 24 hours of storage. So it was expected that we saw large aggregates on this formula. So for the second part, I would like to concentrate on the influence of oil content on rheology. And the relationship that we mostly saw was that formulations with higher oil content, with higher concentration of droplets, they had a higher elastic modulus. And it is, in some references, some authors say that this can be interpreted as a higher stability. If we have formulations that have storage modulus, G prime above G double prime, we have a stable formulation because the droplets within are not migrating not cremating or not sedimenting. And we saw that this behavior, this relationship with the oil content is almost exponential. So here on the x-axis, we have the mass fraction of the formulations. On the y-axis, we have the G prime values within the linear viscoelasticity range. And we see that as we increase the oil content of these formulations, we have higher elastic modulus. One of the measurements was the yield stress, and it was measured by both oscillatory and rotational methods. And the yield stress is also one variable that has been used to assess whether or not the formulations are stable. However, we saw that the error is very large for this calculation, and it's even larger for the rotational measurements. So here on the oscillatory method we have on the x-axis, we see that it is more precise. This is the distribution of the values, while for the rotational methods we saw a larger distribution, which we identified as being less precise than oscillatory methods. However, the error was so big that we couldn't take any useful information from the yield stress. The cohesive energy is a calculation that is calculated using the yield stress and the deformation of the material. And we also thought that it would be a good parameter to visualize, to determine the stability of these formulations, but the error was very big, and we saw no correlation to stability and no significant difference between formulations. So we also couldn't extract any information about stability that could be correlatable to the cohesive energy. Now for the frequency sweeps, we saw a similar relationship. It seemed that for formulas with a higher oil content, they had a stronger network, and this can be seen by these two graphs. On the left, we have formulas A, B, C, and D, and on the right, F, H, and I. And we see that as the oil fraction increases, we see both moduli are increasing. They have larger values as well. And here, the relationship between oil fraction and the complex viscosity of these formulas, we see that they are more viscous as the concentration of droplets increases, but there was no correlation to physical stability of these formulations based on the complex viscosity as well. In the third part, I'd like to explain the differences of the rheological parameters over time. And here we see on this graph, on the x-axis, the storage time, on the y-axis, the yield stress measured by oscillatory methods, and in all batches and all formulas. So here we can see that the yield stress does not show any trend of changing over storage time. The solid line here represents the average between all the values, and the dashed line represents the plus or minus 1 standard deviation. And we can see that all of the formulas don't show any trend of oscillatory yield stress over the storage time, and the differences between them are not very significant. So over time, we saw no relationship to the yield stress, and also we could not conclude that the formulation, the creams, had different properties using only this parameter. We did, though, saw some difference using the frequency sweeps. So here on the left, we have the formula A. On the top left, formula A batch A, and the bottom left, formula A batch B. And we saw that over time, they actually have an increase in both moduli. And this can be explained by either the crystalline phase that is surrounding the droplets becoming even thicker, which would create a more resistant structure, or maybe the dispersed crystallized phase is also increasing in size, which will also result in a higher resistance of the structure. So from 1 day to up to 28 days of storage, we saw that 1 day of storage usually is a lot smaller. The G prime and G double prime values are a lot smaller than in 28 days. And some authors say that this is a maturing step of the formulation, that it can take up to 14 or 28 days. The crossover frequency, which is the cross between G prime and G double prime on frequency sweeps, also did not show any relationship with storage time. We can see that is very linear. There's not a visible trend here. And it does not allow us to conclude anything as physical stability goes. Now here are the power law parameters that describe the frequency sweeps. The parameter A is a parameter that is relatable to the strength of the interaction between the droplets, and the parameter Z is a parameter that relates to the number of interaction between droplets and its surrounding neighbors. We can see that the same relationship that was found in the other experiments, we found that the strength of these interactions is higher when you increase the oil fraction, but the number of interactions does not change a lot. And over time, we see that there is an increase of the strength of these parameters, of the interaction between droplets. That could be explained by dehydration or the other phenomena that I explained earlier about the thickening of the surfactant layers on the droplet, on the interface between droplets, between aqueous phase and oily phase. So finally, for the rheological thermoanalysis, which was the most important experiment in the project, we performed 10 temperature ramps, consecutive temperature ramps, at constant frequency and a constant shear stress. And we observed the profiles for these creams as a function of the temperature cycles. Now here on this graph, we have 2 consecutive cooling ramps for different formulas. And we observed that for these 3 formulas, A, B, and C, the temperature dependency is very small. For formulas D and H, we see that the temperature dependency is a little bit bigger. And here, these points shown in black are the points where the elastic modulus and the viscous modulus are inverse. So we have elasticity under viscosity. And this can indicate that the structure of the cream is completely destroyed, in this case at temperatures above roughly 38 degrees Celsius. For formulas with even higher oil content, we can observe that this temperature dependency is much larger when compared to the other formulations described. And we see that there's also a hysteresis effect on formula F and a little bit smaller in formula I. However, the dependency of these formulas over temperature is much higher, which could indicate that these formulations are less stable than the previous ones. And also we see that at a lower temperature, roughly 35 degrees, 34 degrees, the moduli cross over, which can indicate that they're more sensitive to temperature and they are less stable to temperature. Now we can also see the data in not as a function of temperature, but as a function of time. And here we have consecutive decreasing and increasing temperature ramps, indicated by the gray line. And the G prime and G double prime values were represented by solid symbols and open symbols. And we see that over several temperature cycles, the formulation changes its properties over the temperature cycles. And we see that for formula C, we also have some points that we can observe a crossover, which doesn't happen for formulas A and B. And we can see a trend, a decreasing trend for G prime values and G double prime values here on C that we do not see for formulas A and B. This is the general profile of the formulas. They were performed for every storage time in every batch, but here I'm only trying to show the general profile of these curves. Now for D and H, we see that there is a higher dependency over temperature cycles as well. So here on the first temperature cooling ramp, the G prime value for D is roughly around 3, and then it decreases as the temperature cycles go. And so we try to measure this constant that to see if we could use the calculations to correlate to physical stability of these streams. And then for F and I, we also see a similar relationship, but much more erratic and much more dependent on temperature than the previous formulations. So what was done is that to calculate some parameters that could translate and summarize these experiments, so we wouldn't have to analyze each and single one of them individually, we separated these points in 8 groups. So we have G prime maximum values in cooling ramps, G prime maximum values in heating ramps, G prime in cooling minimal points and heating minimal points. So we had 8 groups of points for each one of these experiments. Now, to calculate some parameter that would allow us to translate these numbers into physical stability, a linear regression model was applied over each one of these groups. So here in orange, this line represents the points that are within the G prime values on cooling ramps and the minimal values. So For each ramp, they have a minimal and a maximum value. So these are the minimum values here. And we calculated the angular coefficient of these regression model, and we called it alpha. And this alpha is an index of how much the formulation changes, these rheological parameters changes over temperature cycles. And this was calculated for each one of these 8 groups for all the experiments over 182 days. Now, another parameter that was described in some other references is to calculate the ratio between these points that I had already explained and the value of the first ramp. So in the first ramp, you should have a very a reference of how your formula behaves, how your sample behaves. And then on the subsequent steps, you calculate how much they change how much they changed relating to the first step. So this C value here is the ratio between, in this example, G prime max, which are indicated by the arrows and the points in blue, and the first G prime value, which is this one. So by having these two parameters, alpha and Xi, we try to summarize these values on a density distribution here. So on the left, we have formulas A, B, and C on the storage time of 1 day, or after 24 hours of production. And here on the bottom, after 56 days of production, we see that the C values, which are that ratio, they're much more narrow. The distribution of these values are much more narrow, which indicates to us that these formulas do not change a lot over temperature cycles. All of those ratios, they are very close to 1. So this indicates to us that the distribution is narrow and these values are not, they're not very small or very large. And we can see that same profile for both 1 day of storage time and 56 days of storage time. The same is not true for formulas with a higher oil content. D and H are here in the middle. We see a wider distribution overall with some outliers, which indicates that these formulations are suffering more changes as temperature cycles go on. And here for F and H on the rightmost panel, we see also that the distribution is much larger and we have more outliers. Now here on this graph, we are showing the relationship of the alpha values, the angular coefficient values, over time and over the mass fraction of these formulations. So here on the top left, in subfigure A, we see that formulations A, B, and C have very narrow distributions, and they are very close to 0. And here for formulation D, we have a wider distribution that is a little bit under 0, not a lot, but it is an indicator of how much the structure changed over the temperature cycles. And we see that after 182 days, the distribution, the amplitude of the distribution becomes a little bit more wide, especially for formula C when you compare to the first day, which can indicate that these formulations, C in this case, can be destabilizing faster than the other ones, at least when compared to A and B. So for the final considerations, I like to say that the temperature swing test was somewhat quicker to predict the physical instability than classic accelerated tests. So here on the left, we see that the profile of these curves, it's somewhat correlatable to the phase separation that was observed macroscopically and after centrifugation. And the difference between the methods is that one takes 1.5 hours and the other takes 14 days. So that should be a sign that maybe these tests can help us assess the stability of the formulations prematurely. The other rheological parameters, such as the crossover frequency, the yield stress, cohesive energy, and the profiles of G prime and G double prime did not presented important relevant information in determining the cosmetic shelf life stability. And they were all conducted for formulas that were stored at ambient temperature. So we see that rheology is able to characterize these formulations, but not to predict their stability over time. We also discussed that and concluded that the formulations were very stable due to the formation of the thick surfactant layers on the interface, and likely a gel structure that fixated the droplets in place and prevented them from creaming or coalescing or flocculating. They're actually all flocculated, but creaming or coalescing. We saw that the droplet size had no influence on cream stability over time. And as a final conclusion, we think that to start to implement these methods, we need a much larger number of samples and different materials and different formulations with different properties and different raw materials composing them. So I'd like to thank everyone from the laboratory, Dr. Hilton Alves de Freitas, who has challenged me a lot, but because of those challenges, I grew a lot and I learned a lot. I would also like to thank Isabela Maria Ferreira dos Campos for helping me a lot in the initial stages of the project and for helping me analyzing results and discussing results and actually performing some experiments in some cases. I'd like to thank Dr. Silvia Guterres and Dr. Karina Paese from the Federal University of Rio Grande do Sul, who provided me with the raw materials and provided some knowledge, formulation knowledge. All my colleagues from Biopol, they have been helpful and very friendly. Dr. Fabio Murakami, who not only helped me become a better teacher on the internship, but also was a great teacher in the graduation. Dr. Agnes de Paula Scheer, who helped me by lending us the high shear mixer from the Silverstone high shear mixer. Dr. Saad Khan, who we cannot see right now, but he's watching us, and for accepting the challenge of being on an examining board in Brazil. Augusto, whom without none of this would be possible, the transmission, everything, the media, the slides, and my parents who are here and also helped me a lot financially and emotionally, and Flavia, which is my better half, that has always supported me and always reminds me of how much I can do and how good I can do things, and that never doubted me. So that's it. I thank you for your presence, and that's the end. Thank you.
Thank you, Lucas, for your presentation. But we received now a new from the department. We are not allowed to have public from this moment at any section at the Federal University of Paraná, so we cannot have public in this place. We just received, I just talked with the coordinator of the pharmaceutical program. So we need to ask you now, if you don't mind, I'm sorry, we just received it now that we cannot have public in this section. So if you want to say something to Lucas, please say it now, because I will just ask you to leave this room. And please, we need to remove the cough break from that central part of where you put some food, because we cannot make to have it there. Okay, but in the second part, when you have the defense of the thesis, the argumentation, we just ask you to please to be discreet as possible, just to not call a lot of attention to us, because we're not allowed to do it. So if you can eat something, and please after we can just leave this auditorium. Thank you very much. So we can have like 10 minutes, and after we can continue with the defense. Podemos começar.
Augusto.
Pronto? Good evening again. Let's continue with the defense of the Lucas Chagas Lima do Carmo dissertation. And now in this part of the defense, we have the argumentation. Let's start at this point with Professor Khan from the North Carolina University. Professor Khan, thank you very much for your attention and to read the work of Lucas. So you have something about 30 minutes to do some kind of questions about the work of Lucas. And thank you again for your participation.
Okay. Can you guys hear me?
We can hear you. Okay.
You can hear me? Okay. So I have some general questions, Lucas. And if you can't hear me at any time, let me know. So one of the questions I had was, when you're doing this temperature ramps up and down, isn't there a thermal lag? Like, you're increasing the temperature in a linear rate and then decreasing it down. So the sample is there's a thermal lag to the sample. Have you thought about that?
Yeah, we okay.
I'm gonna turn off my video so that I can hear better, okay?
Okay. We saw in some cases that there was some thermal lag, definitely. We chose not to perform the experiments in a thermal equilibrium because we wanted to have the experiments run as fast as possible. And still we had experiments that were 1 hour and 30 minutes long. But to have a really fast experiment, we chose not to wait for thermal equilibrium. The lag that we saw was noticeable, especially in the steps we had some 30 seconds between ramps, so this lag would be minimum. But we still saw some effects of wall slipping in lower temperatures that allowed us to see this lag. But we chose not to do anything about it. We just measured the G prime and G double prime maximum and minimum values to assess the structural change over time.
Okay. So you mentioned you saw wall slip. Did you say that? Did you say you saw wall slip in some cases?
Yeah, I saw wall slip in some cases in lower temperatures. And
okay. And then how did you account for wall slip?
I'm sorry?
When you saw wall slip at say room temperature, when you're measuring yield stress, when you're measuring yield stress, did you or G prime as a function of frequency? If you saw wall slip, did you account for it by having rough plates or serrated plates or something like that?
Well, there's a chapter in the dissertation that I described the rheometry gap selection, and unfortunately, with limited resources for the RS1 rheometer that we have here at the university, we only had geometry that was cone plate 2 degrees and 60 millimeters of diameter. And in temperature, in ambient temperature, we did not see wall slip. We only saw in lower temperatures in the thermal cycling test at low temperatures, below 10 degrees. And wall slip was not accounted for because we actually couldn't do anything about it here on the university laboratory because we had no rough sandblasted geometries or cross-hatched geometries.
Okay. So I'm going to talk a little bit about now your yield stress data. So you measured yield stress at what frequency? 5 hertz. Is that what you said?
All the experiments were performed at frequency sweeps were performed at stress sweeps, amplitude sweeps were performed at 5 hertz, and prior to the experiments, I had tested some other formulas to choose which frequency was best, and I tested 1 hertz, 5 hertz, and then 10 hertz, and I saw that the data is not on the dissertation, but I chose 5 hertz because it showed a better profile for the linear viscoelasticity region.
Okay. Okay. So you said you tried 1 hertz, 5 hertz. You tried lower because a lot of times measurements are more accurate if you go to lower frequencies, 5.1 hertz, things like that.
No, we always performed with the same condition for all samples, because we wanted to define a method that would be used for all these formulas. So I thought it was best not to change the parameters of the rheological experiment, so we would have a better relationship between the variables. So if we changed the parameters, then we would have different values that would not be correlatable to other formulas, because we had different experiments for each formula. So chose to always use the same parameters. I guess the question is not exactly this one. So could you repeat the focus of the question so I can understand it better?
Yeah. So what I was saying is that a lot of times when you do these discrete experiments to get the yield stress, having a lower frequency gives you more accurate results. And so if you do that, maybe you have a graph of correlation of yield stress, some dynamic, and you may have had a better correlation that way. I don't know. I'm asking you.
Okay, I understand now. I know that the viscoelastic samples all have frequency dependency, so I did not know that having smaller frequencies would probably result in a better reproducibility of the method.
Okay, no, that's fine. One other question of yield stress. Okay, sorry. So when you have a stress sweep data like you do, we have plotted G prime times strain as a function of strain, and when you do that, you get a maximum, and that gives the yield stress a little bit better. This is an approach we picked up from McCusker and Scriven. Something to think about. You don't have to do it, but you have all the data. So what you would do is you would plot G prime times strain on the y-axis versus strain. And a lot of times you see a very nice maximum, and so you don't have to extrapolate your yield stress. So you can try for one of your data to see if it matches what you're having. Again, this idea came from McCusker and Scriven, and something we liked a lot. So just a comment. Okay. I have one.
Just a second. Sorry. I didn't quite understand the commentary, so I'm asking my supervisor to see if he can explain it to me.
Okay.
Can you just wait a second, please?
What I'm saying is there is maybe a better way of getting more accurate yield stress data from your dynamic experiments. So what you could do is you could plot on the y-axis G prime times strain. So from your stress data, you could on the y-axis plot strain, and on the x-axis plot strain, and then you'll see a maximum, and the maximum corresponds to yield.
Okay, thank you.
Just something for you to think about. I have a couple of more questions. So when you do your frequencies, right? When you do G prime and G double prime frequencies, you do not see a crossover. So that suggests that samples are not really gels, right? So if it's not a gel, then how do you have a yield stress?
Well, in some cases, I don't see a crossover, especially for the first storage time, 24 hours. So I guess that I would characterize these creams as a gel, but in later storage times, we can see that there actually are a crossover. So we classify them as viscoelastic liquids and not gels. The crossover points for the first day of storage, the first 24 hours days of storage, were estimated using the software from the rheometer, but I would classify them as gels in that condition. I'm sorry, viscoelastic solids. I was corrected here by my supervisor.
Okay. I'm done. I'm done. Nice job. Very nice job. I like the idea. I like the idea. Measure the alpha. Figure out stability. Figure out stability. Clever idea.
Yeah, thank you. It was the alpha was actually something that we discussed and decided to do because there's not a single reference mentioning this alpha parameter, but that Xi parameter was something that had been described by Monica Bertensen in a Anton Parr report, and it was reproduced in Mesger handbook about rheology. So I thought that using both parameters would help us understand if the rheological thermal analysis would supply us with some information about physical stability of the formulation. So thank you for acknowledging that.
No, that was really nice. One last comment. I actually was expecting samples like the D and the H to be more stable. So that was positive surprise. Where wall fraction less stable. But anyway.
Well, I can actually try to explain that. I'm not exactly sure what happened, but they were more viscous. They had higher elasticity. But I think that they destabilized, most likely because the emulsion refining step in formulation and the preparation was not effective in mixing the phases. And we only couldn't see a phase separation sooner because it is so viscous that it trapped the oil molecules inside the cream, and they had no room to migrate to the top or form droplets within the cream. So I guess that's the most likely explanation to why they were unstable. They only appeared stable, but they appeared macroscopically stable, but they weren't because homogenization was not sufficient enough to emulsify all of the oil.
Okay, thank you. Okay, thank you. I'm done.
Thank you very much. Do you have any other question?
No, I'm good. Thank you.
Okay,
thank you.
Thank you, Professor Ken, for your precious contribution. We are really waiting to hear some considerations from you. Thank you very much again for your patience. And I want to ask you sorry for the delay you have today to start this defense. Thank you again. And I want now to ask for Professor Scheer to give us her considerations about the Lucas job.
First of all, Professor Hilton, Lucas, I would like to thank you for the invitation. And this area has a lot of challenges, and the emulsion or the cosmetic cream are dynamic, thermodynamically stable, and we must understand well their behavior to face the necessities of the petroleum, food, and cosmetic areas. Nice to meet you, Professor Kahn, and nice to see you again, Fabio. Now, I would like to discuss a little more some points to understand what you did and perhaps some suggestions for next work. Some observations I wrote here and in your work, and you can read later, okay? Let's focus in two main points in the beginning. You must check the different information from abstract and to resume in Portuguese. There are some things.
Yes, yeah, they're different.
Okay.
Okay, I will definitely check that.
Okay, and final of item 2, I think it was missing a paragraph or an abstract about what will be done in your work in the final of the item 2. Yes, I think that there is a missing of a paragraph to say, well, now, so I will do these things, okay?
Okay, so that suggestion would be in the results or methodology?
No, in the item 2, it's the let me see, page, before material methods, all this chapter 2, yes, the literature review, okay?
Okay.
before start material methods, you can
Okay, just
say
give a summary of.
valorize
okay.
your work here, okay? That's only a suggestion.
Okay.
In page 55, I have one on 55. You describe a very interesting things here. Yes, in figure 5, okay?
Figure 15.
Yeah, the last paragraph of page 25, and the next one is the figure 5, okay? You discuss this for a long time. It was presumed the cosmetic screen product will emulsify wax, okay?
Yeah.
Okay. Do you believe that you are working with these systems, then emulsion?
I'm sorry?
Do you think, or do you believe that you are working with this type of extraction, then emulsion?
I
in your-
think that with the polarized light microscopy, we can definitely see that there is some buildup of surfactants on the interface of the droplets, and I didn't show exactly the other dispersed structures because I couldn't find them.
Okay.
But it is widely described that these liquid crystals are present on these types of formulations. I had very little time to perform the polarized light microscopy because we don't have an easy access to it. But I think that if we perform more investigations, we could find those structures. And I believe that these surfactants, the cetylceryl alcohol, do form these types of structures. Cannot be completely certain now that if they produce these bilayers that have branches and whatnot, but
Okay.
I think that it is widely described, and I think that this happens.
Thank you. And going now to material methods, you explain the table 1. In your work, it's not so clear about table 1, but now your presentation you explain very much. I'm in perhaps you can you see the table 1, page 44?
44.
Yeah. So all this formulation, the only change is the proportion of water and oil. Yes.
Yes.
The other one is the same. So, do you think about the critical micellar concentration about this polar wax?
No. I'm sorry, the critical concentration?
Yeah, the critical micellar concentration, because you state 10% of polar wax. This is the surfactant, yes?
Yes, it's a blend of polysorbate 60
Okay.
and cetylceryl alcohol.
But
I don't know
you-
exactly at what proportions they are mixed because it's a industry secret,
Okay.
but I didn't define the critical
Okay.
micellar concentration. This formula was actually changed from the national form
Yeah.
of the Brazilian Pharmacopoeia. The original formulation is 15% Polavax, and there is no mineral oil added to that
Okay.
in the original formulation. It is used for creams and lotions, and for lotions the concentration is roughly 7.5%.
Okay. So the mineral oil you added to the formulation, yes?
Yes, I added because we needed to find a way to destabilize these formulations without changing the concentration of the Polavax, because if we reduce the concentration of Polavax, the rheological properties would be completely different. They would be much more liquid than they actually are.
Okay, understand. And in page 45, where the conductivity and pH measures for dilute samples? Why you have to dilute them? You don't have a equipment to do the directly in your samples?
Well, the pH
pH
could
and
have been done directly on the sample. But it depends on the electrode. Some have the sensor that is very, they're inner sensors, and if we try to put the sensor on the cream, it wouldn't fill up enough so we can measure the pH. That was the case for the conductivity measurements. The electrode had an inner sensor, and there was no way to put cream inside the electrode so we could measure it. And diluting 10% is usually what is done for these formulations, both in the cosmetic industry and pharmaceutical manipulation pharmacies.
Thank you. I worry about one thing. It's your difference in the batch samples. The batch samples sometimes are very different.
Yes.
Because we need this be so the same. But what do you think
Well,
this?
there is on page 51, I wrote 3 paragraphs trying to describe why that happened. I think that the most significant difference between batches was the cooling rate in the cooling step of emulsification. And at the beginning of the project, we thought, well, maybe we should try to improvise a reactor so we can have a fixed cooling rate, so we wouldn't have these difference between batches. In the last paragraph of that section, I say that, well, the difference is not necessarily a bad thing. Because, okay, if I have, my idea for the project is to have a positive control, a negative control, and then everything in between. So I could try to find the rheological parameters and other parameters to correlate to stability. So is it bad having different batches? It depends on your point of view. I think it was bad because I don't have enough robust data to make assumptions. But I think that despite having these different batches, we found some relationships with rheology to physical stability.
Yes, you did. You did. So, in the page 15, you say that for these systems, let me see. Never occur as long as never. Do you agree with this never?
Page 50.
15. For these systems, the last paragraph.
Page
Yes. For these systems, it is possible that creaming or sedimentation never occur as long as the soil likes to.
Okay.
And you repeat the never. Do you agree with this never?
I'm trying to look page 50, 50.
Yeah.
Last
The
paragraph.
last paragraph. Yes. I think so.
Never. Okay.
Strong.
Never occur as long as. Okay. Never occur as long as the solid-like structure of the cream remains unchanged. I think that it is a bold statement to make. It's very bold to claim that never. But I think that maybe on the text is not clear, and maybe I just made a bad statement. But the idea was that creaming or sedimentation would never occur as long as the solid structure of the cream remains unchanged. And I took that idea from the concept that if you have polymers stabilizing the emulsion, then if the polymers are in a high concentration, then the droplets will never come close to enough together to coalesce. Now, there are other mechanisms of emulsion destabilization, like ozone ripening, which do not depend on the physical distance between the droplets. So I think that this statement is actually wrong, because coalescing is not the only mechanism that causes emulsion phase separation.
Okay.
Thank you for noticing that.
And And page 53, you say that the emulsion type was defined macroscopically by observing the migration of water diluted droplets to the top of a dispersion.
Mhm.
Could you explain this?
This means that, just let me annotate this part. This means that the emulsion type, whether it is oil in water or water in oil, was determined by diluting in water and observing where the droplets would migrate to. If they migrate towards the surface, then it is oil in water type, and if they migrated to the bottom, then it would be a water in oil type. I'm sorry, that's not
Yes.
exactly true, but that was the
The idea.
the
Okay.
reasoning behind the evaluation.
Well, page 63. Now you are studying a diameter. 63. Let me see. 62, 63. When you are explaining the maximum diameter, and you say that you, without a solution of mineral oil, so this recipe without mineral oil was an emulsion?
Well, then we go back to defining. There was a misconception that I had explained that creams are emulsions. They're not just emulsions,
Okay.
right? They have other structures. There are colloidal systems that are much more complex than emulsions. They can have the liquid crystalline phase. They can have vesicles. They can have bilayers. And probably when I was writing this, I still had that concept in my head that they are emulsions. Now, they probably are, because even if I don't have mineral oil in the formulation, I have other oily components like octyl stearate and that other one, dimethicone, which is an oil, and I think that those are the two main ones.
Thank you.
Octyl stearate and dimethicone.
Okay. So, and on page 64, there you are discussing figure 22.
Uh-huh.
Figure 22 in the page 64, yeah? In
Yes.
the last paragraph, you say, from figure 32, it's possible to notice I has higher GI, etc. Both higher than all the formulas. Do you see this? Okay. This can be explained by the higher oil content of the formulation. But C is not
Okay,
a
I
high-
have a mistake here.
it's not a higher content of, you can, and E, and such as E, there is no patch of E, né?
Yes.
So you have to see this.
Yeah, I
again.
have to change that. What
Okay.
happened was we had a formula E
Yeah.
as well, and it was removed because some of the rheological experiments were performed
Okay.
wrongly for the formulation, so it was removed and it was renamed. So I have to fix these
Okay.
these problems here.
So, in all your work, we conclude that the cosmetic emulsions were characterized as having a time-dependent behavior, okay? You agree with this? So, okay. And in your final considerations, I don't agree only with one of them. Then you changed your final consideration in your presentation, yeah?
Probably.
Yes, you change a lot, but it is good. But let me see the page 85. Your final considerations. The second one, yes, the second one. Take a look at this one. I think coalescence is not one of the consequences of homogenization inefficiency. How could you solve this inefficiency for next time?
How could I solve this? Well,
Yeah.
I think that this is something that I kept from the dissertation and from the presentation. But in some cases, I could macroscopically visualize phase separation while homogenizing. Okay, so I could have done something to assess that problem, but I chose not to because I didn't want to change the parameters of emulsification between batches and between samples. I think that there are two things that should be considered for. I'm sorry. The question is to what could I do to prevent coalescence during homogenization?
Yes, or your homogenization inefficiency.
Okay. So, as I know that you are a chemical engineer, I know that you know a lot more about this than me. But I did some research on homogenization equipments.
Okay.
And the one that I used, which is the Silverson L4RT, with the cap that I was using, the square hole high shear mixer, it does not have a it does not have like a pedal to mix and increase the turbulent flow of the liquid inside the beaker. So what could have done is, okay, the first thing I could have done was to increase the velocity, increase the RPM, because what it does is it pulls liquid from the bottom and it shears over the square holes and it pushes them outward but not upward. Okay. So what happens is that you don't have enough turbulent flow to guarantee that the oil that is constantly migrating to the top to be mixed with the rest of the system. So adding a paddle to increase the turbulent flow would help, and also increasing the RPM would also help because it would increase the turbulent flow by pushing with a larger velocity to the walls of the beaker, and then this liquid would go downward and upward and would create this better homogenization system.
Okay. Yeah, perhaps Boticário can show you a better.
Perhaps.
Yeah. So written here in the second one, I think this stabilization occur likely due to, when mixing the formal components and not because of coalescence. But coalescence is a manner to this stabilization. So you can see this phrase that is not so okay here. So, and finally, what do you think to do next to solve some issues you detected? You had a good results in to preview instability, but you work a lot and you perhaps have something to do different for the next time or for the
there are
AGG?
several things. There are several things that I wished I had done differently. The first one is mainly produce better batches. Having better batches would help a lot in finding the relevant variables, rheological variables. So this would help a lot. Now, there are other things in rheometry that I obviously thought about more, like choosing a better geometry. The cone plate geometry is perfect for measuring viscosity in liquids, but it's not very used for oscillatory rheometry. It can be used, it's not wrong to use, but since you have a defined gap that you have to use, then you should use a plate-plate geometry with a higher gap, because in some cases I had droplets that were over the gap of my rheological experiments, and that's it causes some questioning from people that really understand rheology. And then other things like increasing the sample size. I don't think that longer periods of time, like 182 days was 6 months. It took over a year to perform all the experiments. But I don't think that it is necessary to evaluate the formulas to this much time, but having a bigger sample size. And one thing that I didn't do, because I hoped that the batches would be very much alike, I didn't perform the same experiment 3 times. I don't have any triplicates in my dissertation. And I think they should be done, because just simply scooping out some of the cream to put on the rheometer changes the structure of the material. So if you do if you at least do it 3 times or 2 times, you can be certain that that profile is the right profile, is the accurate profile of the sample. So there are several things, methods of calculating parameters, methods of several things that I could have done, but I think that these are the most important ones.
Thank you.
Thank you.
Thank you, Professor Scheer. We want to thank you also because you did a very deep read in the document, so you found some kind of problems. Mostly, I should say, page 50 and 64. It is my fault also, because I read the document, so I should see such things. But it's easy to correct, to fix it. So thank you very much for your considerations. And now I want to thank you again to Professor Murakami. So please, you have 30 minutes for your considerations.
Well, thank you. Firstly, I would like to thank for this invitation, Professor Hilton. Thank you, Dr. Kahn. Thank you, Dr. Scheer. It's a pleasure to be here. And first of all, I would like to congratulate Lucas for your presentation, for this challenge, being here, and talking in English. So yes. It's very different. So now it's to be great to hear. And now you have a different thing. So you have different things. So
yeah.
Other peoples
yeah.
do not accept this challenge.
Yes.
Okay.
So I think not.
Thank you for all. I have some marks for your work. In general, you have a beautiful work.
Thank you.
In this topic, cosmetics, pharmaceutical science, it's a beautiful work. So I have one question. Why is work is so important for this field?
Well, something that I did not discuss widely in the presentation is the reasoning of the project. Why? Actually, this project came from a demand from the industry. It wasn't something that we developed. It wasn't something that we were striving to reach. So, Grupo Boticário came to us to one of their workers came to us and showed us this experiments that she had read in some articles, some books. And we see that if a project like that comes to us, to the university, so we can develop it and understand it, I think it has it is very relevant in the industry. Now, something that I did not present did not show in the presentation is that if we take, on average, if every formulation needs 90 days to assess the stability, physical stability, and we have a method that reduces those 90 days to maybe 2 days or maybe a week, the human resources that are used to assess stability for hundreds of formulations, because that's what happens. In Grupo Boticário, they formulate hundreds of formulas each year, and they all have to be tested. And the time resources that takes to assess the stability of these formulations is huge when you have a time of up to 90 days of stability assessment. So if we find a way to reduce that time, then that will directly change the costs of stability assessment. And also, this too, if we can prove in the future that it works, can be used for scaling up. So if you produce, I'm going to scale my batch up, we can try to predict the stability of the scaled up batch and not waste raw materials, not produce more waste in the industry. So I haven't explored these as much as the time it takes to assess stability, but I think that there are some applications also in raw material waste.
Yeah, that's it. That's what I'm looking for in your text. This question is just for it, you know. And in the general introduction, I was looking for this question, for this answer.
Okay.
You know, when I read your work, I would like to see about how the industry and the factory, the cosmetic industries, could be this work so be important for this thing.
Mm-hmm.
You know. So the general introduction, I think, is missing some results, as not results, is missing some literature review. Okay.
Okay.
And also in the abstract, I have some points. I'm wondering about the formulas, 7 formulations. Yeah.
Yeah.
This is hard to me to see how the formulations can affect, you know, the rheology and the other things, the physical chem parameters.
Mm-hmm.
So I think you should, in your text, use letters, but you could provide the percentage of oil.
Okay.
You know, it's more suitable to read. No, I do not need to seek the percentage. So it's just little things. Okay.
Okay. Okay.
And in the literature review, I also would like to see about cosmetic industry, you know,
Mm-hmm.
and how emotions could be affect for that reasons, you know. So I think it's okay, it's very nice, but something is missing. Okay, I just did the mark here, so you can sit
Okay.
with your supervisor and make the corrections.
Okay.
Okay. So another question: what kind of for emotions for the in cosmetic industry? What kind of behavior the cosmetic industry looks for the emotions? Do you understand?
The kind of behavior.
Yeah. Which one?
In which aspect? What kind of behavior? I think that the best way to answer that is by explaining what I see in quality control inside the industry.
Mm-hmm.
And what is usually done is that the behavior that they look for are more prone to, sorry, not that's the wrong word. What they're looking for is sensory properties. Mm-hmm. It looks to me that this is more relevant for products, for cosmetic products, like odor and color, see if those changes over time, if they change over time, because in most cases, these products will not spend 6 months in a shelf. They will be sold much sooner than that.
Mm-hmm.
So they're looking for more likely chemical instabilities that could change the odor and the color of the products and spreadability. And I think that this is what they're most interested in when in the quality control department.
Okay. And I'm a little curious about you make your work with an emulsion non-ionic, okay, Polavax.
Yeah.
Do you think it's Lanet? Okay, do you know Lanet?
Yes.
Do you think as ionic or anionic emulsions could affect the whole thing of your work?
I hope not. I hope to to make this method applicable to all types of emulsions. That's the objective. I mean, we shouldn't have to change the parameters of the rheological analysis too much to assess different formulations. But Lanet, I think that it could affect, because of course that the wax, they're all temperature sensitive. So some may be more temperature sensitive, some may be less.
Okay.
So the behavior over temperature cycles can be different. The behavior of the rheological parameters may not be different, because it depends mostly on the mechanical properties of the emulsion. And they're all different, okay. But the wax, the Polavax, seems to be very sensitive to temperature changes.
And in the same way, do you think it's the oil could affect the whole thing?
Yes, definitely.
As vegetal oils, you know, grape oil, seed oils, almond oil. Do you think how the thing is going to work?
I didn't put a lot of thought into this, because I was more focused on understanding rheology, because it was really hard at first. But definitely it can affect. I don't know how it can affect, but we know that different oils have different thermal properties. We have different oils have different chain lengths, alkylic chain lengths, that could affect the stability mechanisms. But I really didn't put a lot of thought into this, because I wasn't expecting to change the formulation on the project.
Okay, on page 44, table 1, you have the letters, and I'm just curious, you know, why letter E is missing? There's some reason for that?
Yeah. Yeah, so what happened was, again, with the problem with batch reproducibility, I prepared A, B, C, D, E, F, G, H.
Okay.
And I prepared 3 batches of Formula E as well. But what happened was, Formula A, the original one, not the one that I presented here on the dissertation, when I was preparing it, I was weighing all the materials, and I was using a scale that was not properly calibrated. And aside from that, I also performed some rheological experiments with the wrong frequency. So I chose to remove A from the dissertation, and I turned E into A, because they were the same oil concentration. So removed A, turned E into A, and then I discussed the results based on that. And I made some mistakes, because I forgot to replace in some letters on the dissertation. But you can see that E is missing, and then G, H, and I are not in order of oil concentration, because actually when I was homogenizing G, which is the one with 70%, approximately 70% of oil phase, then it had separated phases before I could complete homogenization.
Okay.
And then I had to correct H and I, which would be 80 and 90%, to have lower oil concentrations, because I thought that maybe 70% is the limit that this emulsifying system can accept.
Okay.
So I had to reformulate them, and so because otherwise I would lose the formulations.
Okay, on page 49.
Just
Okay.
on the final document, I will correct those problems. I just didn't correct them now, because on my head, F is the one that is, that one, H is the one is that, but in the final document I will go from A to G.
Okay, no problem. No, that's okay. No problem. On page 49, I'm curious again, on the table 2, okay, you says that formula I, okay, it took 56 days, and the microscope days, you didn't do this analysis? What happened
No,
here?
I should have put a legend there,
Okay.
but when I put the hyphen there, it means that I did not see physical separation, phase separation.
It is stable. It is stable here? No.
Yeah, and table 2.
Table 2, okay, but when you didn't do this analysis.
No, I did
No?
it.
You
I
did?
mean, macroscopically, after 56 days, I didn't see macroscopic phase separation.
Okay.
I need to put a legend here
Okay.
to make it more comprehensible.
Well, the batch reproducibility is okay. Nah, it's not too easy to make some emotions.
Yeah.
It's hard. Well, on page 56, could you explain me what is a waxy liquid crystal? I'm not familiar for this term. What is, you see the first topic 442, okay? You says, it was possible to observe through polarized light microscopy that creams contain wax liquid crystal. What is this?
So in page...
Page 56,
yeah, page 56. So,
this second phrase.
yeah, so on page 26,
Okay.
figure 5, there's a diagram of the structures found in creams, cosmetic creams.
Okay.
So the waxy liquid crystal, I'm referring to the structure represented by lowercase c, lipophilic gel. And these structures, they are organized, they're structures that are formed by aligned cetostero-alcohol molecules, and that form lamellar structures, and they are characterized as a liquid crystal because I'm sorry, it's going to be really hard to explain that in English.
That's okay, no problem.
But I know that you know a lot of DRX methods, and
Yes, that's it.
and they can be characterized by DRX, no, XDR, X-ray diffraction, and they can be characterized. One of the references by Jundinger in 1984, which was the reference that I used to explain these structures, he characterized these structures by X-ray diffraction and other methods. And he claimed that these structures, the hydrophilic gel and the lipophilic gel, they are these, they're formed by these crystallized waxy molecules, but their organization is not specifically a crystal, it's more like a mesophase, a phase between liquid and solid. So that's the explanation of the whole thing, because the organization of the molecules is not specific enough to characterize as a solid crystal. So it's a liquid crystal or a mesomorphic phase.
Nice answer. And on page 68, okay, table 6, the formula C is very, the result you obtained is very different.
Yeah.
Can you tell us why, some reason? Can you explain why this is different from these other formulas?
Well, firstly, I thought that maybe the dispersity of the droplet, the size distribution of the droplets would be narrower for this formula. So the hypothesis was that if I have a monodispersed emulsion, then the organization of droplets would be so locked that the yield stress would be higher because it takes more force to destroy the structure that is very organized. But that was not the case. I thought that this would be the case, but it wasn't. The size distribution was just as wide as the other ones, and I really don't know exactly why this happened. Some other explanations could be maybe due to dehydration, or it has less bulk water phase, which flows more easily. But I don't know exactly why one batch of the Formula C had a really high yield stress.
Okay. Yeah, because the percentage of mineral oil is 25%.
Yes.
And D is 35. It's
Yeah.
10% plus. So, well, there's some reason, I don't know.
For some reason that I don't know as well.
Oh, finally, the last question I'd like to ask you, do you think your work, you can change 90 days stability for 2, 3, and 4 days stability? Do you think your work, you can go through Boticário and see, this is my protocol, and you can hire me, or not fire, hire me? What do you think about this?
Well, in the presentation I showed you 8 references about this methodology. I think that is still too early to say.
Okay.
It is still too early to say. However, I believe that there may be some signs that it can be used. Now, Brummer, in his book in 2006, he published a large-scale study with hundreds of formulations, both of the pharmaceutical, cosmetics and food industry, where he found that formulas that had a higher variance of G' and G double prime in higher temperatures, so higher variance in higher temperatures, destabilized a lot faster than the ones who had no variance on these values over temperature. There seems to be more people studying this right now. There seems to be. The last reference that I found was from 2019 by Kekic, and they compared this methodology, the temperature cycles test, to a freeze-thaw test that was performed on climatic chambers. So you put 24 hours at 40 degrees Celsius and then 24 hours at 5 degrees Celsius. And they found that this test, the rheological test, was significantly comparable to to freeze-thaw test in climatic chambers that takes over 15 days. So there seems to be more people studying it. We of course need a lot more studies on this subject, and with bigger sample sizes, with bigger time of analysis, with different formulations. But Isabella from Boticário was here today, and they were always very interested in the project.
Okay.
And I think that perhaps this is something to evaluate. They have the capacity to evaluate hundreds of their formulations. And if they only use some of the workforce to do that, I think that they will come to satisfying results.
Okay, nice work. Once again, I'd like to congratulate Hilton. Thanks a lot. It's a pleasure to be here. Okay.
Thank you.
Thank you.
Okay, thanks.
Thank you, Professor Murakami. Thank you for your considerations about the work. We should say that some things you ask us, we discussed it
Yes.
a little yesterday or last Friday, and we need to manage things to be the document much more clear. Actually, we are looking for a grant for a new student to continue the work of Lucas. So we discussed fastly today with Boticário Group just to see if you can have some kind of grant for a student to continue this project. And we are trying just to increase the number of samples and to see if you are able to establish some kind of relation between this parameter with the rheological stability, with the classical stability, and we want to do it maybe this semester. Thank you very much again. So in this part of the defense, we want to ask to the people to leave this room because we need to discuss the situation of Lucas. I just want you to stay here, if you don't mind.
Okay.
Because now we want just to know if Lucas is approved or not. Just a few minutes.
Shut down the YouTube transmission.
É 20